Dr. Kenneth F. Harris II was recognized by Forbes as one of the world's youngest and most impactful voices in science. He's a senior project engineer at the Aerospace Corporation, where he helps defend satellites from physical and cyber threats for both NASA and the Department of Defense. Dr. Harris previously led the integration of the James Webb Space Telescope's main electronic payload, making him one of the youngest African Americans in NASA's history to lead such an effort. Beyond aerospace, he's a TEDx speaker, STEM advocate, and host of Seeker's Elements series. The title of his talk, 13 Billion-Year-Old Photograph. Please join me in welcoming Dr. Kenneth F. Harris II.
What's up, brother? Appreciate you, man. Thank you. So I'm sure that several participants will agree with my statement here that I am a huge fan of music, all kinds of music, but in particularly classical music. So imagine with me that you are trying to appreciate a symphony, but only through the perspective of one or maybe two instruments as they're being played. This is similar to what it's like to explore the universe or look at the universe through one lens, through one specific wavelength that our eyes can actually appreciate. As we know, present day, there are a vast number of wavelengths that we can appreciate. And so what happens when you can then hear the full symphony? Or in this case, what happens when you can actually see and start to unravel some of the mysteries of the universe? Let's go and throw the first slide up if it's not up. Oh, it is. There it is. Boom. And so today, we get the opportunity to talk about one of my favorite topics, and that is images that come from distant galaxies. We know that we have data that dates back to over 13.5 billion years within the universe. So today our story begins in 1800 with a German-British astronomer by the name of Sir William Herschel. Sir William Herschel's studies was about an invisible source that was around us, right? He had this desire to observe the sun with his naked eye in a telescope and some really well thought out filters. And so what he did was he put his thermometer, his barometer, at the end of what we know as the red wavelengths, the shortest wavelengths that we're able to see, and that thermometer continued to increase in temperature. What that told him is there is some invisible force acting upon this that I cannot see. It was later coined as dark heat, which we know now, present day, as infrared light. Infrared light, infrared technology is what has helped us to kind of comb through the universe and uncover some of the greatest mysteries that we previously did not know. And so again, I want to say good afternoon to everyone. This talk will be a bit different than what you typically see at Craft. I've had the fortunate opportunity to work within this industry for over 17 years. I started when I was 16 years old up there at NASA Goddard Space Flight Center. Since then, I've worked on 8 different programs, all the way from rocket science to observatories that explore our distant universe. So this talk today is about the meeting point of our mechanical systems and our software-based systems that help us get the telemetry down and dissect what those zeros and ones, the binary code that we get back from these from the studies of these distant universe and galaxies really means. But first, I need to explain to you a bit about the mechanical systems, a bit about how our human anatomy actually works and processes information, and then the huge data sets that we call telemetry when it comes back down to us. And that's me at Craft last year. So quickly, if anyone saw me at QCon this year, anyone from QCon? Okay, don't spoil it for anyone. It's kind of the same thing. Anyone saw me at Craft last year? Great. Okay, so this is an expansion of what we talked about at Craft last year. So last year we talked about the alignment of our mirrors, how we set it into space, and then we are ultimately able to point it at certain points and dissect that data. Today we're going to talk about the mechanical systems that allow us to dissect that data just a bit further. So for those that did not see me at QCon and did not see me last year, what is he talking about? I'm talking about the James Webb Space Telescope. That's an artist's rendition of a flyby for the James Webb Space Telescope. This is a massive, massive project. It took over 2 decades to build, $13 billion. This is us integrating it at the Johnson Space Center, This is the Johnson Space Center, and this one's over in California. If you can't tell by now, I am American, and it's okay to feel bad for me. It's okay to feel sorry for me just a little bit here. And so the James Webb Space Telescope, my absolute favorite program that I got the chance to work with, right here on the left, on my left, your right, you're going to see Brian removing our lens cap here. And this lens cap is important because that little hole there is where all the light from the universe actually goes into and funnels into the back of the system, which is where all our instruments are. And I'll get into that in a bit. Just keep that in mind. On the front, gold mirrors, light goes in there, processed through instruments, to the antenna, to the ground station, to the systems, to your eyeballs. It's kind of the process flow there, all right? All right. So this is something I haven't done at at Craft before, but we'll try it out. And so in the universe, like I mentioned earlier, we explore wavelengths, right? So wavelengths are how we are getting this data. Short wavelengths, kind of medium-ish wavelengths, and long wavelengths. Let me put this down for this next section here. No, I'm holding. And so when you think about the variations in wavelengths, we know from studies that it goes all the way from gamma rays down to radio waves. So your really short, excited photons, all the way down to your really less excited, we call them older photons, for lack of a better term. But in the universe, we know two things. We know a lot of things, but for today, we're going to talk about two things in particular. One, the universe is constantly expanding. The universe is not stagnant. We know that two sources that were close by billions of years ago are no longer in that. Take away the variations of gravity and blah, blah, blah. Just in general principle, they aren't next to each other. They have separated. And we know that the light source from those planets, galaxies, shifts as a function of the galaxy continuing to expand. This phenomena is known as cosmological red shift. It's fun to bring up at dinner parties if you want to impress your friends. Cosmological red shift basically means that from a light source, the wavelength is going to get longer and longer and longer until it's into the infrared light and you can't see it. For the sake of today, I want to do a quick, visual aspect of things. So for today, we're going to use our camera operator here. I'm going to pick on him. He's going to be our light source within the universe, all right? So he is cameraman 3023X. I made up a name, all right? Cameraman 3023X. And then this gentleman in the blue, with the blue tie here, he'll be Earth, okay? He'll be what we're trying to observe it from either the ground station or from some orbiting satellite. So what I'm going to do is break you all into three groups really quickly, and we're going to emulate what it's like for a wavelength to travel from our cameraman to our Earth. It's really easy. If you can clap your hands, if you can hold a beat, it's going to be really, really simple for you. All right, so three groups. My first group is in this row here, so everyone in this set of rows and the beanbags over here. Middle group is going to be everyone in this section, and last group is over here. Okay, so three sections. I want you to do it with me here. We're going to count in sets of 8, okay? For all my musical people, this should be really easy for you. So my first group, it goes 1, 2, 3, 4, 5, 6, 7, 8, okay? We got it? Middle group is going to be on the 1, 3, 5, and 7, okay? So 1, 2, 3, 4, 5, 6, 7, 8. Got it? Anyone hesitant? All right. Last one over here. Last group. You are the oldest section. No offense. Oldest section, shortest wavelength. So you do the 1 and the 5. So 1, 2, 3, 4, 5, 6, 7, 8. Okay? First group, you're going to do it 4 times. Middle group, you're going to do it 3 times. Last group, you're going to do it twice. Okay? So we're going to start with you. 1, 2, 3, 4, 5, 6, 7, 8. On the second time, you all come in. Second time for them, you all come in. Got it? Get it, got it, good. Ready or not? Here we come. Ready, first group? Here we go. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Thank you. Thank you for indulging me. Thank you for indulging me. So this is just a quick, typically I bring like a camera and there's all kinds of light shows and things like that, but for today, we're going to use sound. So this is how a longer wavelength, really attractive photons move toward a much shorter wavelength. And what we did within these 3 bands, so remember these 3 sections as 3 bands, when you're looking at light and wavelength, we can break them down based on our own anatomy and own physiology, that then we can then overlay that with filters on the system, algorithms in our software to then emulate the light that we would see if our eyes were functioning within deep space. okay? So young wavelengths all the way down to our older ones, and we'll talk about that in a bit. Just hold that. And that is how we come up with images like this, all right? This is a spiral galaxy. This is one that came from the Hubble Space Telescope. You'll see a lot of blues, a lot of purples, a lot of oranges or reds kind of in that. This is shot mostly in visible light. And from that demonstration, what I want to see from like the symphony aspect is that you need each section to understand the entirety of what's being given to you from the universe. So this is infrared, this is visible light. But when you overlay it with additional studies that we have from infrared light, you see a much deeper representation of the universe. Much darker colors in terms of reds. You can see dust plumes in it. You see kind of a centralized star there. And that's because infrared light, our shorter wavelengths, are able to break through dust clouds in the universe and allow us to see them in much more depth. And this is how we discover which of our stars are older and which of our stars are younger. Our older stars typically come red. Our younger stars are typically bluish. Okay. So remember what I said earlier, the gold mirrors on the front are how we process the image how we process light. So think about the James Webb Space Telescope as a bucket, okay? And it's absorbing all of this light. So the light from the universe comes in, hits those gold mirrors, bounces off those gold mirrors into what's known as the secondary mirror, which is a boom at the very end of our observatory. That secondary mirror then bounces into that light source that Brian was uncapping earlier. The light bounces in there and into our instrumentation suite on the back. Our instrumentation suite has 4 instruments on board. It's a mix of 6 different subgroups that I'll mention very briefly here. And from there, we're able to, again, process it through onboard readers, communication antenna, down to our ground station. The satellite's split into 2 sides, hot side and cold side. This group today, we are biasly cold side because that's the side that I worked on. Cold side is the top of the observatory, has all the instrumentation, it has the mirrors. Everything south of the sun shield is the hot side. It's about a 16-meter difference between these 2 sides. And the differentiating factor between them is the cold side is probably negative 165. The hot side is plus 235-ish. I'm talking Fahrenheit. And so that 16-meter difference is what differentiates the hot side and the cold side. And we have to function this in a really cold environment in order for us to utilize this satellite and for the satellite to not have interferences. Because, as I mentioned earlier, Sir William Herschel was experimenting with heat. And once you get kind of beyond that the red wavelength, what you see, you don't see heat, but what you see is heat. And heat can disrupt the data that you're getting. Okay. I mentioned earlier, you've got 4 instruments on the back of this guy: near spec, near cam, MIRI, and then our last one we just called NIRSI, which is really more like a GPS type system. For any of my space folks out there, this is where you'll get your PNT data, which is your position, navigation, and timing for your satellite. So how we know where it is, what orientation it's in, things like that. And those come down to you in satellite data packages we, again, know as telemetry. So commands go up, telemetry comes down. That's the general flow of how satellites work. And so, again, I'm trying to breeze through this mechanical stuff because y'all don't care about mechanical stuff, but we need to understand it in order to get to the software stuff. And so 6 subgroups. I want to make sure I get this right, so I'm going to step up here quickly. So 6 subgroups that you have within your observatory that make it tick and talk, right? And so each of these instruments that I mentioned, the 4 instruments that I mentioned, have some mesh of one of these, or some of these 6 elements. So you got your aperture mask, which basically acts like, imagine like you're looking at a star at night, and there's a street lamp in the way, so you make a cutout on like a cardboard and block out the street light and just look at the source that you're looking at. That's what an aperture mask is in this situation. Micro shutter array, one of my favorite parts. We have over 248 little trap doors everywhere on James Webb that we're able to mechanically open and shut based on the commands that we send up. This allows us to explore multiple spots of the universe within a swatch all at one time. And when I say explore or observe, I mean the light sources from them, I mean spectrograph searches from them, which allows us to examine the molecular structure or the molecular values of what we're seeing back from the atmosphere of these planets or these galaxies. The third one is going to be your integral field. And so your integral field unit is basically a diagnostics on the pixels within the data that you get. So how are you interpreting what each light source means? And from the perspective of that molecular structure that I mentioned earlier, is there hydrogen in the atmosphere? Is there oxygen in the atmosphere? Is this an exoplanet that can be found within the Goldilocks region, for example, which could potentially hold life? And then we have our spectrographs. So our spectrographs are you are diagnosing kind of each wave that comes in for you, and you can drill down into the intensity factor of each wavelength that you're seeing, whether it's short wavelengths or long wavelengths. You got your coronagraphs. Coronagraphs are really key to exploring exoplanets, as I mentioned earlier. We know that for exoplanets, you must be within, again, what's known as the Goldilocks zone. The Goldilocks zone is an area around a central star that's just the right distance that we could have potential life on that planet. Coronagraph allows us to put this mask, it's the flip of an aperture mask. You put this mask over the sun, and you can see what is around that star system. So you see a lot with our sun. If you've ever seen kind of solar flares off the side of the sun and things like that, that's through the use of a coronagraph. And then lastly, cameras. We all know what cameras are, so I don't need to explain what a camera is. But on James Webb, we have 3 cameras. There are 2 infrared cameras and 1 there are 2 near-infrared cameras and 1 mid-infrared camera. Again, think about the 3 bands for infrared that we'll get into a bit later. Just kind of hold that. It comes in 3s, okay? So 2 cameras. This is a quick swatch of what I was just talking about in terms of your instrumentation. So each instrument you have is broken down into the segments as the microns that it can observe, and each instrument does something different. So MIRI, for example, is great at shooting some of the coldest exoplanets or some of the coldest galaxies that we've seen. So any of the planets that you see with rings around it typically come from MIRI, because MIRI is able to shoot in that kind of micron that we actually see dust rings around the planets and the systems. Spectrograph camera, integral field unit, coronagraph. NIRCam is like the superstar of this observatory. It's the only one that has that coronagraph and an actual camera, which means it's the only one that can observe exoplanets. So any of the exoplanets you see coming in data sets from James Webb came from NIRCam. Next one is NIRSI. Like I said, we typically use it for GPS reasons. It does have a camera. It does have spectrographs, but typically we use it in any of our data packages that come down with They come down with calibration data and comes down with that PNT data set that you see. Next is going to be NIRSpec. Again, similar to NIRCam, but a spectrograph on it instead of just that camera that I was saying. And so this has our micro shutter array that I was mentioning earlier, so we can see a large swatch of the universe all at once through NIRCam. Typically, NIRCam and NIRSpec are shot in the same general direction or through the same profile, and because you want to know more about the galaxy than just the age of it, for example. And so why do we have different instruments? We have different instruments because you're able to build different profiles. This is something that I'll get to toward the end, in about 10-ish minutes of the end of a presentation. All of this data that I'm going to show you is publicly available information, publicly available data. And so research groups, universities are able to make proposals to say, hey, I'd like to utilize these 3 instruments pointed at this section of the galaxy so that I can study cosmological redshift to Z to the 12th or something like that, whatever it is. So this is an example of light as it enters two of our instruments. One of the most fascinating parts you'll see here is NIRSpec is going to split the light into 30 different filters. Those 30 different filters will then return to you the values of those wavelengths based on the profile that I was just mentioning that you built. And so based on the profile that you build, you can turn filters on and off. You can specify if you just want to see young universes or young galaxies versus older ones. And so I think that's a really cool part about NIRSpec that you're able to drill down into. Okay. So everyone knows what I mentioned earlier in terms of what we are able to see, the visible light spectrum. People are very familiar, at least in theory, with the visible light spectrum. So we know Roy G. Biv. Technically, it's Roy G. Biv, if you want to drop the I out, because we know that Sir Isaac Newton had a fascination with the number 7, 7 C's. In Western music, there's typically 7 notes, 7 original planets. And so he kind of smushed indigo between blue and violet. But within the scientific community, we typically acknowledge Roy G. Biv. For James Webb, they do have a filter specifically for cyan, which will come between green and blue as well. So remember this when we're talking about the profile of what our eyes can see. And what we see is it's not really primary colors, but we see kind of in blocks. And so you see in 2 ways. You have cones and you have rods. And so your rods allow us to see through 3 major colors. That's red, green, and blue. Okay, so if you ever hooked up an old TV or a VCR or DVD, it's got connectors in the back, red, green, and blue, typically, or your component cables are red, green, and blue. That's because it's meant to emulate the composition of us. It's meant to emulate our eyes. And so we know that by combining these 3 colors in any fashion, you're able to make any color within our world, and is exceptionally the universe as well. And so what do rods and cones and all this have to do with how we see the universe? Great question. So, rods. Rods are how we interpret grayscale, so blacks to whites, okay? And then overlay that with cones, and that's how you see colors, your red, green, and blue. And so this is where things like, damage to cones come in mind when it comes to color blindness and things like that, where you have damage to your cones. I bring this up because these layers, this kind of image stacking, this kind of filter stacking is exactly what James Webb does when it processes the information to you, and what our team does when we then take these filters and layer them one on top of another to showcase to you these images. Because, spoiler, it doesn't look like this when we get it, right? It takes some artistic rendering to extrapolate the data and say, well, this color is red, this color is blue, this color is orange. Okay, so you have the visible light spectrum, and what you're gonna do is, here's how you make a color picture in space. You have 3 bands. You've got 1 band to the left, you got 1 band to the right, and you got 1 band in the middle. For the sake of our exploration of infrared light, that's known as near infrared, mid infrared, and far infrared, okay? We overlay that with the visible light spectrum so that it is juxtaposed to say that your shorter, more kind of volatile protons are your blues, your purples, those kind of colors. Your middles are kind of your greenish, your yellows, things of that nature, and then it shifts in kind of your orange and reds in your much shorter wavelengths. And so this is meant, again, to emulate how our eyes perceive light, because our eyes, in this case, are the bucket that photons go into, just like James Webb is the bucket of photons that the light from the universe comes into. And so, again, we're seeing through that RGB perspective. So what does that mean in the sense of taking that data, applying it to a filter, getting that filter in some form of data set to the satellite back to us? So these are the filters that were developed specifically for the James Webb Space Telescope. Some of them are used on Spitzer as well. But like I said, you have your shorter wavelengths all the way to your your shorter wavelengths all the way to your longer wavelengths. There's 29 different filters that are featured across the satellite. These 29 different features stacked one on top of each other is what helps us to create these images. So keep that in mind. Not every time you take a shot of the universe, you don't use each one of these filters. It's based on the profile that you want. You can use all of them, or you could use a few of them. Each of them have specific characteristics that help to align with your specific research's goals. And that's part of the beauty of being able to build your profile. That's why we work something like this into the program. Okay, so how do we go? Where are we at? How do we go from an image like this to a fully rendered image like this? So same exact image, same exact picture of a swatch of the universe. This is what's known as the Spider Nebula. No spiders included, I promise. It's known as the spider web for kind of the cloud, the kind of webbed cloud around it. And so, like I mentioned in probably every slide we've got here, it's through image stacking. It's through utilizing your filters one over top of another to identify what's green, what's what's blue, what's orange, what's red, what's yellow. And we're actually going to do an example of what one of that looks like. And I'm going to walk you through utilizing our online systems. I'm going to walk you through being able to develop a actual image, because if you want, you can go and do it in your own time as well. Okay, so one of the things that you'll care about on this program is specifically our file format and the products that we receive from the James Webb Space Telescope. This is an example of when I was originally making this video. I downloaded a data package, and this is essentially what it looks like when it's unzipped. You typically, in this file you didn't, but you typically get 4 types of files. You get a FITS file, a JSON file, an ESCV, and an ASDF file. So your FITS file is going to be your largest file that you get. When it comes to put in perspective for you, the James Webb Space Telescope has scheduled downloads every 12 hours at our download stations. Each of those downloads takes 4 hours apiece, based on how much data that is gotten. We have, I think we set the limit around 60-ish gigs for the solid state that it has. But at any given time, it downloads that, circles back around the Earth, does it again, circles back around the Earth, pointing into the universe, does it again. So any typical day, most of your larger files are going to come through your FITS file, and that's your I2D FITS file, which is going to be a third from the bottom, not your segmented FITS file, which is more so like your ASDF file. So these huge download data packages are typically in the FITS file because that holds much of your data pixels. So when I say data pixels, actually visual, what you can see. You can see, oh, I see a larger star over there than I see over there. That physical imaging that you get from the James Webb Space Telescope is factual. We're not color coding that. Those are all factual. When it comes to the JSON file, don't need to really get into what that is, but the general gist of it is, for this program in particular, is we use it for calibration regions and to know specific outputs around the instrumentation that was used on this program or on the profile that was being developed. Your ESCV file, it's like a glorified Excel file, for lack of a better term, has a lot of your metadata, your photometric information. For any of my photographers, videographers out there, it'll have those metrics for the profile that you built in order to then shoot that section of the universe. And then lastly, your ASDF file is, again, it's made up of metadata from that profile, but it's oftentimes rolled into the FITS file because it's specific to the filters that I showed earlier. Of those 29 filters, that's typically where you find it in that ASDF file. So of that download that you get every 12 hours, that takes 4 hours, we land somewhere around 50 to 60 gigs per download, and that's every 12 hours. And so, but a lot of this, and I meant to pose this at the beginning of this talk. James Webb was developed at a time, specifically in the early 2000s, where we weren't thinking about really leaning into AI as much, just because of the runway you need to put something like that on a mission of kind of this caliber. And so when it comes to the fluff that you get from a 60 gigabyte download package, and you'll see in the example that I give you, a lot of it is just static noise. So from the perspective of utilizing AI, from the perspective of being more efficient, how can we improve our system so that maybe a download package isn't 20 gigs of just static noise, and maybe we're actually getting everything that we actually need within each download that we get. Just something to consider for anybody that's looking at the space agencies or space industry and thinking, how can my organization fit in? There's a huge need there for the efficiency aspect of what we're doing when we get data packages. This is an example of what you get from FITS files. Again, calibration pipelines, your data sets, your instrument configuration, things of that nature. And I will give you these, and I'll give you a set of QR codes at the end that'll take you to more information about this if you want to learn about it later. Just trying to speed through this. Okay, so making a full color image. We talked about this image stacking. You assign them from shortest wavelengths, from shortest wavelengths all the way to the longest wavelengths. So you start with your blues, your greens, your orange, your red, then you get your full composite image. All right, so and I'm gonna try to run this from just the clicker, so bear with me. So through a combination of our NASA team, a brilliant astronomer I know by the name of Nico Carver, and again, the team at NASA and Johnson Space Center, put together this really short video, a series of videos that kind of explain how we go to our mass system. We pick a star system that we want to look at, and then we're able to extrapolate the data from there. Because I do not believe in live demonstrations, because technical difficulties always happen. This is pre-recorded. I'm going to talk you through it. Right now, so what we're going to do, we're going to explore what I like, which is the Carina Nebula, NGC 3324. So once you can pick almost any star system, right? Based on if you know the name of it, or you can look up the name of it. This guy over here is our astro view. It allows us to, and once it loads, it'll make more sense. But every project that has ever shot in that direction is going to populate its data there. So any project, James Webb, Hubble, Spitzer, TESS, anything that's shot in that direction, it will populate there. We can filter it based on what program we want. So for today, we want the James Webb Space Telescope. You see, it's a much smaller swatch of what we actually looked at. Or you can go back to Spitzer. It looks, different, obviously. And so you see the Spitzer data is around 3,000, which is because it's been up there forever. So James Webb, you actually click on the rectangle of what you're looking at, and it shows you in real time which of the data packages you need to replicate that specific section of space. Again, this is just an example. This is called the Carina Nebula. You can do almost anything. You can do exoplanets. You can do the whole gamut of things. So specifically for today, we just wanted science data packages, so I clicked on science data package. But if you can see, I'm scrolling kind of fast, but you can do different images. You can do specific instrumentations on the project. You can do not just science data packages, but you can do health of the satellite, or you can do calibration of the satellite as well. And so this is a pretty extensive database that, again, is free. It's public information for you to have. If there's a little lock next to it, that just means that the research organization has first dibs on the information, and it'll typically be let out in about 3 to 4 months for you to use at that point. And so shrinking the astro view, you can see that if you scroll over I'm going to edit the columns, but before I get there, under the filters right here, those filters from that mapping of the colors that I showed earlier, that's the data set that was shot through those colors, or those specific, or that's the data set that were captured for that length, that wavelength, okay? And so you can tell just from looking at that, if you knew the graph well enough, you could say, well, this has a bunch of short wavelengths, for example, or this has a bunch of really long wavelengths, so a lot of old stars within it. And so this is just an example of something you can do. That button there is going to download that whole data set package for you. And once we unzip it, it'll look like what I showed you in the former slide. But what you need to do is you download it, it's going to load, and then you actually have to do that for each data package. Again, is a filter, so you have to do that for each filter in order to overlay it. Okay. So once that's downloaded, and again, I'll give you the resources to this. I like to use PixInsight, but there are other ones. There's Surreal. There's a number of different astrophotography platforms that you can use in order to make images like this. A lot of them have functionalities built in that will take your data set and make it linear, for example, or take your data set and stretch the data points so that you don't have to do all that. They have things such as, and I'll let it play in the background. These are things that they'll let you do the star alignment within it as well. So once this guy gets open, you see all these, I can't pause it, but you see all these files that are coming up in front of us here. These are all, they're actually empty. They're black, right? They're static. Some of them are static noise. As I click through them here, like some of them are just calibration files where the satellite's not perfectly lined up. You can see kind of in the staggered approach there. So we're just going to close that one. Close that one. Okay. And same thing there. You're just making it linear. You just see a bunch of static noise with kind of each of these that you got. So as I continue to close each of these, close. Okay. And same thing, static noise. So this one in particular is just not calibrated perfectly. But you can still see that it's starting to take shape of what we're looking for. So if you've ever seen the Carina Nebula, you might recognize that this is an upside-down version of the Carina Nebula. And that's because in space, there's no up, there's no down. So you can take some artistic liberties here to flip the photo based on what you believe the consumer will best recognize. And so this is a picture. This is an actual raw image that we get from the James Webb Space Telescope as it looks through a specific filter. I think this one is filter F335, which tells me it is a shorter wavelength. So these are going to be older, redder stars. And so, again, I'm clicking that button. That just makes all your data linear. It balances, it makes it linear. Again, a quick shortcut that you can use with this astrophotography software here. Once you have that, keep in mind, this is just one image in particular. I'm just zooming into it so you can see the finer details of it. But let's move on to the next one here, because I have to leave time for questions at the end. So once you get through that, you have to go through and download each data set, okay? So each filter that you have, the F335, the 221, the 21, you have to download all of those because each of those has, again, in this symphony that is exploring this pocket of the galaxy, each of them contributes data to your overall picture that is the universe. So again, open up a ton of basically empty files, that calibration files and things of that nature, because we can be a lot more efficient with what we're doing. And you finally get to this one, which again, you balance, and you see that this one is a little foggier, right? We know this is foggier because it is shorter wavelengths that cannot break through dust clouds in the universe, so it's a little foggier than your longer ones that you can actually, your redder ones that can see through wavelengths. And so you can kind of see the juxtaposition of them just side by side. What I'm going to fast forward to next, again, can't do it with a clicker, so I'll talk through it as I'm doing it on screen here. The next thing you need to do in terms of the image stacking process is actually do what's called a star alignment. And so star alignment, when I get to that part, is I'm going to flip both the images. I'm going to stack them on top of each other. PixInsight allows you to actually highlight a specific portion of the image that you're trying to see, and it'll actually do the alignment in the back end. Because again, you have to think about, this is James Webb looking at the same spot of space, just taking multiple photos through multiple lenses. And so it's your job to just align it and then go from there to then add the light on top of it. Okay, so again, quickly, going to mirror that, flip those both over. Let's get to, skip that part. You pick some interesting points that you want. You can crop it if you want, but for the sake of this, you don't need to crop this. I was doing extra. I got a little into it. Okay, so that's cropped, and sorry, I wish I could speed this up, but I only have a clicker. Okay, so the next part, I'm going to highlight this. Okay, I'm going to highlight this section. It's going to then overlay the star system for us. Then we get to what comes next. Okay, so what comes next is PowerPoint. Surprise, right? Surprise, surprise. We actually use PowerPoint. We can use other images. We can use other softwares too if we'd like to. But for this example, we're going to use PowerPoint. And so you see here on this side, I've stacked all the images from shortest wavelength to longest wavelength. And what you do is we're going to identify which of the filters we used for this experiment or for this particular profile. We use the images or the filters that are shown here. That tells us there's a data set that shows you the hex codes, like a range of the hex codes that you can use as well. And so this is an image of the filters that were actually used. So working through this really quick, it stacks. What you're going to do is you're going to go through each one, you're going to assign the color palette to it. Once the color palette is assigned to it, you move on to the next one. All of those are going to stack together into a composite image. There's some blending involved. I won't get into the whole thing, but there's some blending involved to it. And then from there, again, it's some artistic kind of freedoms that come with, is it a deep blue? Is it like a really, really deep blue, or is it like slightly closer to purple, for example? And what you'll see in examples of astrophotographers online, such as Nico and Ravel and things like that, is that they actually have variations in the colors that NASA has assigned to them, or ESA, or the European Space Agency has applied to them, to what they actually perceive it as. So again, it's up to the artist in some ways, but at the same time, we have kind of a base level of what we're going through those filters that have been assigned. And so once we get through all of this, I won't jump through this today. Once we get through all of this, the image that comes out is something like this. This was known as the Carina Nebula. It is a cosmic cliff. It's the is actually the edge of a gigantic stellar nursery that a lot of our young star systems are born in. That's why you see the top is really a deep blue, majority is blue, while that bottom part is mostly these dust clouds that are peering through, that you're peering through the dust clouds for the red, but you can also see little dots of blue and yellow, which are all indicative of younger star systems. So this is a stellar nursery. Typically, stellar nurseries exist anywhere between 50,000 to 100,000 years. This Carina Nebula for us is 100 plus light years away, so it's nowhere near us. It's nowhere near us, but we're still able to image it thanks to great technology and understanding infrared light in the universe. And so jumping into other images that we're able to establish from, thanks to our understanding of the James Webb Space Telescope and the universe. Does anyone know what this is? Does it look like anything in particular to anyone? No? If I turn it this way, does it look like an animal, a familiar animal at all? It's a penguin. It's called the Penguin Nebula. And so it's so creative with the names. So this is the Penguin Nebula. And it's an example of, again, a profile that was built specifically to observe young stars within the galaxy. Why do we want to do young stars? In this particular instance, they were really interested in these bottom galaxies here. Do I have a laser? Yeah, these two kind of bottom galaxies here. And then this really, really bright one here is what believed to be actually not even the birth of a star. It's supposed to be the death of a star. And they flagged it as the egg that the penguin is watching over. NASA or European Space Agency has a huge sense of humor, I guess. All right, and this one here is about 2.5 light years from us. Two of my favorite images is what I want to show you next before we land this plane. On your left, my right. It's called the wreath. It's supposed to be like indicative of a Christmas wreath, for example. You have the outer layers, which are red, even moving toward that kind of inner layer, which you see, again, those really, really old star systems. Some you see kind of younger star systems near the bottom and around the sides there. But this one all the way at the top there is the most fascinating one. And that kind of bluish light is almost in the initial interpretation of this. It was said that star system was misinterpreted to be a lot younger than it actually is. And so there was a number of critiques around this image in terms of why is it so blue? Why is it as large as like a spirit bomb for all my DBZ fans? So we're looking into why that is the way it is. This one on my left, you're right. I included it because I was talking to a good friend about this presentation, and they're a medical doctor, and they say, hey, that looks a lot like a hair follicle under a microscope, right? And there's some appreciation to how there is a commonality between the sciences, between what you see in the universe at a universal level in comparison to what you see at kind of the microscopic level. To put this in perspective for you, this is known as the cosmic tornado. It's over 9 light years tall. So it's, and for all those that don't know what a light year is, about 6.9 trillion miles from top to bottom. In terms of a light year, not this, that's 9 million. And so this cosmic tornado is one of the newer images released in 2025. One of the cooler images that we have there is part of the Herbig-Haro object. And kind of right on the tip of the tornado, again, a younger galaxy that is starting to be born. So again, by utilizing these layers that are from the James Webb Space Telescope, you're able to interpret all of these different pockets of the universe. And so getting to the point, the 13 billion year old image. This is an image of what's known as SMACS 0723. It contains some of our oldest star systems that we've ever discovered in the galaxy. You got 3.1, 3.0. You see, to date, we haven't done the kind of in-depth study of what it looks like really close. But we know that these star systems could be 13 billion years or older. And so, again, the name of the star system, SMACS 0723. Does anyone know how we get the names for these star systems? No one? Okay. At NASA headquarters, we got this huge whiteboard of names. What we go through is any name that Elon doesn't pick for a kid, we assign. I'm joking. I'm totally joking. But it's typically from how large it is, what the image contains, and ultimately how far away it is, or juxtaposition to other images in the galaxy. So really quickly, another visual for you to end. Stick your hand out like this for me, in front of you, if you will, like this. There you go. One index finger out. At the very tip of your index finger rests a tiny grain of sand. This image, all 40,000 galaxies, planets within it, you can put your hands down, rests within that tiny grain of sand. And so this is an example of what it means to live in the universe that we are in. There's much more work to be done. There's more galaxies to discover. There's planets to be discovered. We need to just move forward in a more efficient manner within the space agency, within the space industry, and all of you are our partners within this. You see, it's still scrolling out. And so just that tiny grain of sand, again, will reveal that 40,000 plus galaxies and images that we have. With that, that's my time. I'll turn it over to Alex for quick questions. Appreciate you all's time. Thanks for hanging out. Oh, and resources up here. If you want to build your own image, is there, and then you can connect with me on LinkedIn.